Vancouver's Griffiths E&M section 3.4.1, example 310. So far we have been trying to find the potential of some charge. Here's my pen. Charge Q. We can write down as, at some point in space, which is a distance r away, we can write the potential as 1 over 4 pi epsilon naught, the Q of our charge, over the distance. I can also say, all right, well, I don't know exactly what that single charge looks like. Maybe if I look close enough, it's a series of distributions of charges, or it's a distribution of charges, some assembly of discrete things. And I can say, all right, well, far enough away, I can still write that the potential at that point in space is 1 over 4 pi epsilon naught. They're all roughly the same distance away, and it's just the sum of all of my individual charges, which is the same thing as saying that that's related to my total charge Q. It looks very similar to this expression. In fact, we don't actually know how the charges are made up for these point particles. We just assume that they're point particles. Now, what if I have two charges? Let's say that one is a minus Q and one's a plus Q, and I want to know what the potential is at some point in space. These above expressions would tell us that it's related to the total charge of my distribution, 1 over r times 0, because that's my total charge. But is that really true? That seems unlikely. Okay. We have a tool to deal with here. We're going to eventually introduce the multipole, but first we're going to talk about the first new element of the multipole expansion by investigating this scenario a little closer. So I have my two charges. Let's say this one is now, for my notes consistency, that's going to be a plus Q. This one's going to be a minus Q. And they're going to be a distance d apart from each other. I'm going to define the midpoint here just as some special center. There's no charges there. Okay? And I want to evaluate the field at this point. Okay. I'm going to say that that from the midpoint to the point I'm evaluating in, I'll call that vector r. And then the vector that points from my negative charge to that point, I'll call that script r minus, because it's from the minus charge. And then I'll call this one from the positive charge, script r plus. And I'm also going to define a couple angles here. I'll call this theta, not correlated with the polar angle. I haven't defined what the orientation of this two charge arrangement is. And I'll call this alpha. Right? Alpha and theta are going to be related to each other because the sum must be 180. Okay. So I can more generally write that potential at this point in space as 1 over 4 pi epsilon naught times minus Q over the distance from the minus charge plus Q, the distance from the plus charge. Now let's go ahead and rewrite what these script r vectors are going to be. Okay, so script r plus, I'm going to use the law of cosines here. Script r plus squared is going to be equal to the two bits of our triangle. So r squared plus d over 2 squared. the side of my triangle. I'll highlight this in red just to make sure we're all good. That's the triangle we're using right here to calculate that. Minus 2 d over 2 r cosine the angle. Okay, I can go ahead and say, all right, well, I know that d is going to be small. Oh, well, I did do it. I missed a spot. All right, I'm going to go ahead and pull out an r squared. Okay, that's going to give me 1 minus d over r cosine theta plus d squared over 4r squared. All right, that is equal to that. Those two lines are exactly equal to each other. All right, and I'm going to go ahead and say that this is a line I tried to get earlier, that this is approximately equal to r squared times 1 minus d over r cosine theta. All right. I'm acknowledging the fact that d is much, much smaller than r. Okay, that's what script r plus squared is. Now I need script r minus. Okay, I'll try to create some space over here. Script r minus squared, still using the law of cosines. The first two terms are the same. Minus, I'll just go ahead and write dr here. Now it's the cosine of the angle between them, which is alpha. Alpha is just 180 minus theta. They're related to each other. You put in a 180 minus theta into here, you use some trig identity, and you get r squared plus d over 2 squared plus dr cos theta. Okay, so the same exact, very similar looking expression. All right. I can go ahead and pull out an r squared here. 1 plus d over r cosine theta plus d squared over 4r squared. And again, write that that's roughly equal to r squared 1 plus d over r cosine theta. Okay, so now I have an approximation for what each of these unit vectors, or each of these script vectors are. All right, now I remember that the potentials have I'm gonna have to go to a new page for this, but I remember that the potentials all look like something 1 over script r. Right? I'm gonna need to find out what 1 over script r is for each of these vectors. Okay, so I'll rewrite over here that script r plus squared is approximately equal to r squared 1 minus d over r cosine theta, and script r minus squared is approximately equal to r squared 1 plus d over r cosine theta. Okay, so to get the value of 1 over script r plus, that's going to be approximately equal to 1 over r, taking the square root. I'm going to go ahead and leave this top bit on top instead of inverting it to the minus 1/2. Okay, so I've taken the square root. That's what the 1/2 comes in, and the minus is because I'm inverting it, but I'm leaving the term in parentheses in the numerator. Okay, then I can do the same thing for script r minus. 1 over script r minus is approximately equal to 1 over r times 1 plus d over r cosine theta to the minus 1/2. Great. I'm going to apply now the binomial expansion. which says that 1 plus x to the n, if x is small, can be written as 1 plus nx. Okay, in our case, x is this term in our expression, and n is going to be minus 1/2. Right, and we know that x is small because d is much, much smaller than r. So I can rewrite this as 1 over r plus, is approximately 1 over r times 1 plus d over r, 2r cos theta. Right, I expanded that square root out. And the same is true for script r minus. That's 1 over r, 1 minus d over 2r cos theta. So now I can rewrite the full expression for my potential at a point r. That is equal to 1 over 4 pi epsilon naught. I have my positive charge q over 1 over r plus 1 over r plus is just 1 over r times 1 plus d over 2r cos theta plus 1 over 4 pi epsilon naught minus q, 1 over r, 1 minus d over 2r cos theta. All right, we have a couple terms that look the same. These ones, I'll distribute this negative sign in, so I get a minus, a plus. These ones cancel out because the coefficient up front is the same, and I'm left with basically two of these cosine terms. So 1 over 4 pi epsilon naught q 1 over r times d over r, the 2 cancels, cosine theta, or v of r is equal to 1 over 4 pi epsilon naught q times d over r squared cosine theta. This is the potential at a point in space from a dipole. I have two charges. One's a positive charge, one is a minus charge. That is a dipole. Okay. Notice something interesting here, that the potential that we've discussed so far always decays like 1 over r, but this one decays like 1 over r squared. Pretty cool.